beautiful Mindsetters. It is a Thursday morning and you're hanging out with Looney once again, and I'm with Tracy today.
Hello, Looney. How are you?
I'm good, thank you. How are you?
Good, thank you.
So what are we doing for the Mindsetters today?
Today we're doing chemical change.
All right.
So we're looking at redox, we're looking at rates of reaction, chemical equilibrium, all the things that right now I can just hear the groans. I can hear it. You know, and it's not just the voices in my head, but I can then hear it, yes.
All right. Mindsetters, you heard it. We are doing chemical change for Spring School Grade 12. Remember to hit us up on Facebook at facebook.com/LearnExtra, on Twitter @LearnExtra, and you can download everything that you need to know about today on learnextra.co.za. Just click on the Spring School link. If you want to see the schedule and the notes, just click on their Spring Schools right there on our homepage, Spring School, and you'll see everything that we have to offer for you today. Remember, we do have the competition going on, so all you need to do is stop the clock. So how you do it is that you tag or share the post that I will post on Facebook. It's written Day 4 Spring School, and you tag or share it, and then you put your favorite number 0 to 9. Okay, so 0 to 9. Tracy, can we just show them where the clock is right now?
Got it. There we go.
So it's on 3. If you see there, Mindsetters, 3. Because we're looking at the last digit of our Facebook likes. So the clock is on 3 right now. It will change because we haven't stopped it. So make sure you tag and share that post all day, every day today, right now, this lesson. And make sure that you do that to stand a chance to win that amazing Learn Extra hamper. So with all that said, I'll take it straight back to Tracy.
Oh, thank you. See, it's on 3. And in fact, we've had like 200 odd likes since Tuesday. It's hysterical.
Yeah.
It's brilliant. Okay. So, grade 12s. We are doing chemical change. Now, I know this is a section that sometimes you sort of go, oh, I hate this section. But you know what's nice about it? Is it covers rates of reaction, chemical equilibrium, and then redox and acids and bases and all of those sort of things, okay, that are in your curriculum. But the questions are very similar. So there's only a little bit of theory that you then need to apply, okay? So I need you to be paying attention. We've got lots of really nice questions. Most of them are taken from the February 2013 paper. Some of them are taken from the 2010 paper, okay? So they're nice questions to look at. So we're going to jump right in. We're going to start with rates of reaction. And, oh, it's a bit slow today. There we go. This is from February 2013, question 6, okay? So now what it says to us, it says the apparatus below is used to investigate the rate at which hydrogen gas is produced. So key words here, rate at which hydrogen gas is produced when a certain amount of zinc, okay, reacts with excess dilute hydrochloric acid. Guys, the excess hydrochloric acid is really important. It means that the zinc is your limiting reactant, which means the zinc will determine how much product we get. So if we change things to do with the hydrochloric acid, it's in excess, that might change the rate, but it's not going to change how much we get. But if I change the amount of zinc, so say I go from 10 grams to 20 grams, then I'm changing the amount of zinc chloride I'm going to get at the end. Okay, so let's just look at that. Now it says to us, so we have the hydrochloric acid, the zinc's over here, okay, we have a delivery tube into a really nice gas cylinder, we have a stopwatch, the stopwatch is to measure time, and then they give us the reaction. We like it when they do that. They say to us that 2HCl plus zinc goes to zinc chloride plus H2. We like this because it's balanced, makes life a lot easier. First thing they ask us is write down the name of the flask labeled Z. Now I know you're going, oh, it's been such a long time since I did this. It's always a good idea to make sure you know the names of things. This is a conical flask, okay? It's not a beaker, it's not a round bottom flask, it's a conical flask, okay? So it's a conical flask, and we use the conical flask because we can seal it quite nicely and put the delivery tube through the top, which makes our lives a lot easier. Then they say, write down one function of the item of apparatus labeled Y. So, Y is this. It's the gas syringe. So now think about what the name says to you. I've just said to you it's a gas syringe. We are measuring how much hydrogen gas is produced over a unit of time. So that means the gas syringe is used to collect the hydrogen gas produced. Simple as that, okay? Don't try and be over analytical. look at it from a logical point of view and go, well, what am I doing with that gas syringe? I'm collecting the gas. That's where the hydrogen is going to be, okay? Then, 2 experiments are conducted using the apparatus above, which you've just seen. The conditions for each experiment are given in the table. So they tell me for experiment 1, the zinc is powdered. Experiment 2, the zinc is powdered. Hydrochloric acid for experiment 1, 0.1 moles. For experiment 2, it's 0.2 moles. So the thing I've changed is concentration. Okay? I've kept temperature the same. I've kept powdered the same. Okay, so we're all happy with that. Now, it says to you, from the table above, write down the independent variable. What is the variable that I controlled by changing it myself? Okay, so I'm not looking at controls. Okay, the controls are the things that stayed the same, but what is the variable that changed? And that is the concentration of the HCl. Remember, square brackets mean concentration. So that's my independent variable. I changed that. Then it says name only one controlled variable. So we look at this and we go, well, actually there's 2. One is the state of division or surface area of the zinc. We kept it as powdered zinc. The other one is temperature. We kept the temperature constant. You only need to give me one. Please don't give both. All right, grade 12s, make sure you answer the question as asked. I often see that you just end up writing lots and lots and lots, but by writing lots and lots, you're not going to get any extra marks. Okay, and in fact, sometimes by writing so much, it's very difficult to see what you want as your actual answer, and then you don't get any marks anyway. Now it says, the volume of the hydrogen gas produced is measured in each experiment, and the graphs below show the results. So this is the volume of the hydrogen gas produced. I want you to realize we get the same volume at the end, just at different rates. P has got a steeper gradient, which means this is a faster rate than Q. The gradient isn't as steep, goes slower. Question 1.4 says to us, which graph, P or Q, represents experiment 2? Refer to the data given in the table, as well as the shape of the graph, to explain how you arrived at this answer. Well, let's look at experiment 2. Experiment 2, we increased the concentration of the hydrochloric acid. So now we've got to go back and we've got to think about the things that change rates of reaction and how they change the rates of reaction. Remember that by increasing concentration, we have more hydrochloric acid particles available. The more hydrochloric acid particles there are available, the more collisions we're going to have. The more collisions there are, the faster the rate. Okay? So experiment 2, we increase the concentration of the hydrochloric acid. By increasing the concentration of the hydrochloric acid, I've increased the rate. Okay? Which means the graph needs to be steeper. So in other words, P represents, because it's a steeper graph, here we go. I'm going to get there. It's a steeper graph, okay? So how do I answer this? So we say P, we realize that. So then what we'll say is you need to refer to the table. Well, in the table, and I'm just writing this in shorthand to make it easier, we increase the concentration of the hydrochloric acid, which means the gradient is steeper. And that's what graph P shows us. We have a steeper gradient because we've increased the concentration of the HCl. Okay? Then, give a reason why the rate of the hydrogen production slows down towards the end of both experiments. So what they're asking for here is, let's just get rid of all of this nonsense over here, okay? Is they're saying to you, why is it that as we get to this part of the graph on this one and over here, why does it slow down? Why doesn't it just keep getting faster and faster and faster and faster? Okay, why is it at fast and then it starts to slow down? What you need to remember is for a chemical reaction to happen, we need the particles to collide, and we need to collide with sufficient energy and correct orientation. But we need particles to collide. So as we get nearer and nearer to the end of the reaction, we have fewer and fewer reactant particles. So we're using up the zinc and the hydrochloric acid, and by using up the zinc and the hydrochloric acid, there's less particles available for bonding, and if there's less particles, we have fewer collisions, so the rate decreases. Okay? Hopefully you got that. So what am I telling you? As the rating gets to the end, less particles, fewer collisions, slower rate. Okay, I'm hoping that sort of makes sense. Last part of this question, and I know that if some of you actually have seen this paper before, you would have got to this part and gone, really? I don't remember how to do this. It says, calculate the mass of zinc used to prepare 0.24 decimeters cubed of hydrogen gas at room temperature. Assume that 1 mole of hydrogen gas has a volume of 24.04 decimeters cubed at room temperature. So we're going, oh boy, this is a mole calculation. Or some of you are going, I don't remember doing this yet. Probably maybe haven't done it since grade 10, maybe even did it last year, but last year seems like a mile away. So we're going to do the step by step. First thing, balanced chemical equation. So we have HCl plus zinc gives me zinc chloride plus H2 that was given to me right at the beginning, okay? They want to know what mass, so I put a little question mark there in grams, and they told me used to prepare, and we're going to get 0.24 decimeters cubed of hydrogen. Now we're going to use a mole ratio issue here, okay? You guys might have learned to set this out slightly differently, but it's all the same thing, all right? So stay with me. First thing I'm going to need to do is I need to know what the mole ratio is. So I'm going to put 2 to 1 to 1 to 1, okay, which comes from the coefficients. So 1 mole of hydrogen will be produced from 1 mole of zinc. They tell you that at room temperature, 1 mole of hydrogen gas is 24.04 decimeters cubed. First thing I'm going to do here is work out the number of moles of hydrogen, which is going to be the volume that I've given divided by the molar volume at that temperature, which is 24.04. So in other words, I'm going to go 0.24 divided by 24.04. Okay, and this time, unlike on Tuesday, I have my calculator already. So, whoops, 0.24 divided by 24.04, and we get 9.98 times 10 to the minus 3. I'm going to leave it like that, okay? 9.98 times 10 to the minus 3 moles. Now, it's a 1-to-1 ratio, and I've got a random thing just then. Hey, we've got an eraser on our screen. It's great. Okay, number of moles of zinc. It's a 1-to-1 ratio. So it's going to be 9.98 times 10 to the minus 3. And I just need to quickly make some more space here. Really? There we go. Times by 1/1. They want to see the small ratio. So in other words, I'm going to make 9.98 times 10 to the minus 3 moles of zinc. We can work out the mass of zinc from this, okay? Because number of moles is mass divided by molar mass. Okay, mass is what I want, and the molar mass of zinc, which we read off the periodic table, is 65. So mass is going to be 9.98. Now please, because I know this is what you do, you have this already on your calculator, you now times this by 65 and off you go. Please don't do that, okay? So 9.98 to the minus 3, because that's the value I'm using, times by 65, minus 3 times by 65, once again, gives me 0.65, okay? So the mass, 0.65 grams. This was worth 6 marks on the paper. grade 12, please, 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 and if you've just written prelims and if you wrote the government prelims, you realize this was in there, okay, and you probably haven't seen it for a year. So make sure you know how to do mass, and mole mass, and all those sort of calculations. Very, 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 very important. And I think, Looney,
Yes.
it's time for a break.
Okay. Mindsetters, you are going to take a very short break. Remember to join the group on the Facebook page for physical sciences so that you share your information and your knowledge and ask questions from all other mindsetters and you connect with them and you guys can talk and have a nice fat chat there about physical sciences. We are going to take a break, but don't go anywhere. Welcome back, Mindsetters, from the break. I hope you guys are still, with us and you following Tracy as she's teaching you. I just want to let you know that please tag yourself or share the post, guys. Don't be writing on the wall now and telling us your favorite number. Tag or share the post and tell us your favorite number from 0 to 9. We are going to stop the clock somewhere around the show, not now. So please tell us your favorite number from 0 to 9 and we will announce the winner during our 4 o'clock show. So make sure you watch. Even if you don't do the subject, make sure you watch and then you might be a winner of that very special Learn Extra hamper. So with all that said, Tracy.
Thank you. Okay. So guys, we're going to carry on with rates for a little bit. And I really like this question because what they've actually done is decided to ask you a whole bunch of theory, but to help you a little bit. Okay, so it says to us, and this is from November 2010, the collision theory explains why chemical reactions occur and why they take place at different rates. Some of the terms used in the collision theory and reaction rates are given below. So they give you a list of 8. Okay, so it's surface area, catalyst, effective collision, activated complex, concentration, temperature, heat of reaction, and activation energy. Then they say, give one term for each of the following descriptions by choosing a term from the list above. Now, the nice thing is that even if you're not sure, you can take a guess. You've got a 1 in 8 chance to get it right. It's not like you have to make up anything, but don't make up something that's not there, okay? There's only 6 questions, so you're not going to use all the words, but they're not going to ask you one and then the term's not there. It has to be there, okay? So if you're not sure, guess. And your teachers right now are cringing. At least you've got a chance of getting marks. If you leave it empty, you're going to get nothing, okay? First question. A chemical substance that speeds up the rate of the reaction, so it speeds up rate by lowering the net activation energy. The only thing that can do that is a catalyst. So 2.1, the answer is a catalyst. Nice and simple, okay? A collision in which the reacting particles have sufficient kinetic energy and the correct orientation. So let's look at what we've got here. So we've used catalyst. Surface area makes no sense. It has to be an effective collision. Okay, effective collision, correct orientation, sufficient energy. Brilliant. 2.3. The factor responsible for increasing the rate of reaction, so we're increasing rate when the solid is broken up into smaller pieces. So smaller pieces means we go from big pieces to powder, something like that. That's got to do with surface area, states of division. So we go, has to be surface area. Okay, it's not any of the others. 2.4, the temporary unstable state that is formed during the course of a chemical reaction. That horrible in-between state that we can't do anything with, and that is my activated complex. Okay, so I've already used 4 of these. Okay, so now I'm only left with 4: concentration, temperature, heat of reaction, and activation energy. And we go back down here. So we've done that one. 2.5, a measure of the average kinetic energy of the particles. You shouldn't even have to go look at the list, because this is a definition. That is temperature. Okay? The net amount of energy released or absorbed during a chemical reaction. So we've used temperature. This means the heat of reaction, change in enthalpy. Nice and simple. I put this question in because I really like the fact that it really gets to a lot of your definitions. So it's a really important one. Okay. Oh boy. Now we get to the dreaded equilibrium. Okay. Now, Looney, during the break, you said you had a question with Casey. Do you want to ask me quickly, and then we'll go on from there?
So it's from Duncan Pasha, And he's asking, is it possible that we can be asked to calculate Kc without the volume?
Duncan, we are going to look at some Kc calculations, and if they give you all the values already in concentration, so they tell you what the concentration is, then yes, you don't need the volume, but most of the time they're going to give you volume because you need to work with number of moles. Okay, so it is possible, but most of the time they're not going to do that. Okay, because they like to make sure you can calculate concentration, so they probably will do it. But we are going to actually look at a couple of Kc calculations along the way. So hang in there, keep watching. Oh, we've got another question. I see a hand up. Oh, I like this. We even have a hand up in the room. It's wonderful. Yes, Leni, how can I help?
Kevin is asking, why is it that every time on the graphs of reaction, the reactants begin with a greater amount of moles, whereas the forward reactions don't?
Okay, you're asking why is there always reactants and not products? Because reactants are what we put in, so we have to start with the reactants. The reactants then make the products. We don't start with the products, and once the products are made, they can be reversed and start making the reactants again. Okay, so the reactants is everything we put in. So there has to be lots of that to start off with. Every now and then we might start off with some product, but then that's just be mean, which isn't beyond the examiners, let's be honest, but generally they won't do that. Okay, so you have to start with reactants because you need reactants to make the product.
Last question.
Last question, okay, yes.
This is just a general question for the paper. Will I get penalized if I start with any question? This is from Masekomeng.
Yes.
Wow. If I start with any question during the final examination, example, question 10,
Not
9,
at all.
6, 5, but
Not
then they must be in order, like when you put your papers together. Just
No,
make
not
sure.
at all.
You don't have to?
No.
Oh, okay.
You can start, I would suggest you do question 1 and 2 first,
Okay.
or at least leave the space for it first, but you can do your question paper in any order as long as you keep entire questions together. So don't do 1.3, 2.9, 7.3, don't do that, okay? Start each question on a new page, but if you want to start with question 10 because you looked at question 10 and you say learnt, in this case, say question 10 would probably be your chemical industries question, and you've learnt the chloroalkali industry backwards and you know that like you know it was your own name, then do question 10, but do the whole of question 10. Then go on to whichever question you want next, but don't mix the questions together, but you can do it in any order you want, as long as it's clear. Okay, most of you probably have teachers who have told you that you shouldn't do it like that, and that's fine. I know it's painful. Okay, I hate it. I hate marking it when that happens.
Yeah.
But I also know that sometimes that's the way it's best for the learners.
What our teachers told us is that you can start whichever question you want, but then when you start putting your papers together, like your answers, just make sure you staple them in order to make it better for the teacher to mark.
But you see, it's hard because they get given booklets.
Yeah.
So with the booklets, that's quite hard to do, and you're not allowed to tear your booklets apart. We're not allowed to damage them in any way, and sure, and then they have to be signed for and signed over, and there's quite a big, there's a lot of admin with that, so we don't want to do that.
Thanks.
Yeah. Okay, so equilibrium question. We probably won't get through all of this question before the next break, guys, but it's fine. We're going to take our time. We're going to make sure we get this, okay? Adapted from the 2013 paper, it says to us the reaction between hydrogen chloride and oxygen reaches equilibrium in a closed container according to the following balanced equation. So a couple of things. It's 4HCl plus O2. The reaction shows me that it's an equilibrium reaction. It's reversible. And then they tell me delta H is negative. Okay? Remember, delta H always refers to the forward reaction. So it always refers to it going from left to right. Now, that helps me answer the next question, which says, is this reaction exothermic or endothermic? And they're referring to the forward reaction. So we look at delta H, we go, well, delta H is negative, which means that this is definitely an exothermic reaction. Our reason, delta H is less than 0. Simple as that. You can also tell me that energy is released. We realize that because delta H is 0, but it is an exothermic reaction, and they refer into the forward reaction. Then they say, ooh, the fun part, which is what we were talking about just now. The graphs below, not drawn to scale, show how the amounts of reactants present in the container change with time at a specific temperature. Remember, equilibrium is established at a certain temperature, which means we can calculate a Kc value at that temperature, But if temperature changes, Kc changes as well. Temperature is the only thing that can change your equilibrium constant. And they tell you the volume is 5 decimeters cubed. They tell you that we start off with 1 mole of HCl, we start off with 0.3 moles of O2, end up with 0.1 moles. This is in moles, not in concentration. Okay, so we need the volume, which was Duncan's question earlier. We need the volume to get to concentrations, okay, if we're going to have to calculate that. Now they say, how does the rate of the forward reaction at time T1 compare to T2? Here's T1, here's T2. You've got to look at the steepness of the graph. If I had to take a tangent off here and a tangent off here and compare it to the tangent of this one, over this side, sorry, and over here, can you see that at T2, the steepness, it's not as steep, okay? So the gradient is less, okay? As soon as the gradient is less, the rate is smaller, okay? So it's smaller than, that's the first part of our question, all right, because they asked how does it compare, so we'd say it's smaller than. Reason, your gradient is less steep. That's all you need, okay? Simple as that, gradient is less steep. You don't need to talk about the number of moles of HCl and O2 and all of those things. That's a consequence of it, but that doesn't really help me. It's got to do with the gradient. Now they say, how does the rate of the forward reaction and the reverse reactions compare at T3? T3 is here. What do you notice about the amounts of HCl and O2 that we've got over here? Can you see that now these graphs run parallel to the time axis? Reaction hasn't stopped. Reaction has reached equilibrium at T3, which means that your forward reaction rate over here, they are equal. Okay? They're equal. And the reason we'd put that, sorry, I just want to check the nice science way of writing it. Okay. Well, they didn't actually ask you to explain why, but if they did ask you to explain why, what you would need to say, and please be careful here because it's easy to say, well, because the graphs are not parallel. Yeah, but it's probably better to say because the number of moles of HCl and O2 remain constant. Okay, number of moles of H2 and O2, HCl and O2 remain constant, okay? Which results in the graphs being parallel to the time axis, but we're not overly concerned about that, okay? Now, ooh, wrong way. Again, there we go. Seriously? See, it did this on Tuesday for those of you who are watching. I'm telling you, this board does not like me. Okay, I think we've answered, no, we haven't, okay. Third part of this question, same thing. Now they say to us, calculate the equilibrium constant for this reaction. And I can hear the groans. No, Tracy. Okay. Now, what I think we're going to have to do, Looney, is we're going to need to take a break now. I know it's a little early, but we're only going to get about a tenth of the way through, not even, before we need to take a break again. So I think we're going to take a small break, which means those of you at home that are watching who sort of have an idea of where to go, I want you to start looking at this and how to do it, okay? Because it's best if you try it first, and then I'm going to do it with you.
Okay, cool.
Okay, so I think it's time for a short break.
All right.
Yeah.
Mindset is let's take a very short break, but we will be back, so don't go anywhere. Welcome back, Mindsetters, from that break. I hope you guys are still enjoying the lesson and you're still with us. Me and Tracy here doing chemical change. So Tracy.
My turn.
Yes.
Okay, so guys, the thing we all love to hate. All right, they want us to calculate the Kc Kc constant is what we're going to calculate now. So, important thing to remember is they said to me the volume was 5 decimeters cubed, so that's going to be important. We have the initial concentration of the HCl, which is 1, and we have the initial concentration of the O2, which is 0.3, and we know that the O2 ends up at 0.1. So it's quite nice, we don't even have to try and read those off the graph, it's given to us. Remember that to do a KC calculation, we need to do a rice table or an ice table, okay? Which you've all seen. So first thing I'm going to do is I'm going to remind myself what the equation looked like, because it's a little bit of a complicated equation. So we have 4 HCl, no, I can't copy it. So 4 HCl, okay, I'm just going to write it at the bottom here for me, so I don't forget, a little bit further up. 4 HCl, okay, plus O2, wow, you see it's going to do this all day for me now, plus O2, and it was a double arrow, and it gives me H2 gas, and no, that should be H2O, that's an O actually, that's quite sad, okay, H2O and 2Cl2, okay, so here we go, and it gives me 2H2O and 2Cl2, and I'm just going to just double check that this is actually balanced. I've got 4 hydrogens, 4 chlorine, 2 oxygen. Okay, we're fine, we're balanced. So what we need to do is we need to draw a table. Now remember, the table is going to have 5 columns, okay, 1 for HCl, 1 for O2, 1 for H2O, 1 for Cl, and then the first one, which is where we write all the things we need. So the first thing we're going to need, okay, is we always have the ratio. Now some of you may or may not write this part in, but just stick with me. Then we have to have initial, which we're going to do in number of moles. Then we have change, which is why it's called the rice table. This is the C, which is also a number of moles. Okay, then we're going to have equilibrium, which is also in number of moles at this point. But remember that to work out a Kc value, I have to have equilibrium concentration. Okay, so that means I need a 4th row, okay, well, a last row over here, and this one is my equilibrium concentration, which means this is in moles per decimeter cubed. Okay, hopefully I haven't lost anyone yet. Now what I like to do is I'm going to go, this is HCl, this is O2, then I like to put a double line over here, okay, because I want to remind myself that now I've gone into my products, which is H2O, and sorry, I just actually have to tell you this, Looney, because this is what happens in my classroom. My learners have very, very graciously called this the fearless line.
Fearless line.
Yeah, it's the fearless line because it's mine, and I'm their teacher, Miss Fearless, you see.
Aww,
so we have the fearless line.
No,
that's what
so
we refer
cute.
to it as, and that's my little bit of my moment. Anyway, from the balanced equation, we go, well, the ratio is 4 to 1 to 2 to 2. Right now I'm just filling in everything I know. Initially, we knew that the HCl was at 1 and the O2 was at 0.3. Okay, and at the end, at equilibrium, we have 0.1 moles of the O2. We've just put in what I know. Now what we need to do is fill in the stuff that we can work out. Now the first thing we also always know is that we have 0 product. 0, nothing. Okay? Because we're making product. Then what we're going to do is we're going to go, okay, we remind ourselves that we use up the reactants and we make products. Another thing we need to remind ourselves is that the ratio of the change line and the ratio in the ratio line must be the same. So when I work out the changes, this line must be 4 to 1 to 2 to 2. Okay? So if I start with 0.3, I've ended with 0.1. That means I took away 0.2. Now I need to work out how much goes in the others. So watch what happens. I'm going to multiply by 4, divide by 1. So this If you look at it, this becomes almost like a multiplication sign because of the one in the middle, and that's your division sign. Okay? So it's a mole ratio. Okay, I need 4 times as much HCl as I need O2, have a O2. So I have to go 4 times 0.2, which means I'm going to get 0.8. Okay? And I wanted it as a dotted line so that you could, you would do that in pencil. Okay, so this is 0.8. And now do the same with the H2 and the Cl2, H2O. So now I'm going to go times by 2, divide by 1. So that's 0.4. Times by 2, divide by 1, 0.4. Now, 0.8 to 0.2 is 4 to 1. 0.2 to 0.4 is 1 to 2. 1 to 2. Same ratio. Okay? Now remember, I used up 0.8. So I'm going to go 1 minus 0.8 gives me 0.2. Now I make products, so it's 0 plus 0.4. 0 plus 0.4. Almost there. Okay? But the equilibrium constant says to us that we must use concentration. Okay? So we remind ourselves over here that concentration is number of moles divided by volume. So I'm going to have to go 0.2 divided by 5. 0.1 divided by 5. 0.4 divided by 5. 0.4 divided by 5. So we go, fine, we've got 0.2 divided by 5. 0.04. Okay. I'm actually going to just put this over here. And what I'm going to do now, and this is what I really think you should do in your exams, is I'm going to put this straight onto linear mode so that I don't have to worry about the converting all the time. 0.1 divided by 5 gives me 0.02. Come now. 0.02. I'm going to do the last one. 0.4 divided by 5. 0.08. And both of these are 0.08. Okay. If this is worth 9 marks, no, it's actually worth about 7 marks, you've got 4 already. Okay, the last 3 marks are for actually working out the Kc value. So we've really done the hard part, but please be careful, grade 12s, because as a memory guide, you get taught that Kc is concentration over products, okay, concentration of products divided by concentration of reactants. Grade 12s, this is not an equation, okay? You will not be given a mark for an equation if this is what you write. Because from here, you now substitute values in and you get an answer, and you might get the right answer, but you're not going to get the marks. Please, please, please be careful, okay? You must write it as a proper equation, which means I'm going to take this out because this isn't the equation. We're going to take the reactants of the products, sorry, the concentration of the products, which is H2O and Cl2. So it's concentration of H2O, which would be squared because it's 2H2O, Cl2 squared because it's 2Cl, divided by HCl to the power of 4 times O2. That is the equation. Okay? Concentration of reactants over product is not the equation, grade 12, sorry. Very important that you get that. From here, we now do our substitution. So now we can go 0.08 squared times 0.08 squared divided by 0.04 to the power of 4 times 0.02. And now we all go, now I've got to put this on my calculator. Of course we can. Watch. Okay. If my calculator is going to come, say hello. There's my calculator. All right. So, Okay. I'm going to start, we're going to do it in brackets. So I'm going to do the top part. I'm going to do all of it together, okay? So I'm going to go 0.08. Let's put it all. 0.08 squared times 0.08 squared. That's the first part. Oh, not sign. Sorry. Bracket. That's the top, okay? All of that is going to be divided by 0.04 to the power of 4. There's my power button, okay? And I'm doing it to the power of 4. Let's just go back here. Okay, to the power of 4. Okay, got it? Times 0.08, all close the bracket, which gives me 8,000, which it wasn't supposed to give me because I made a mistake somewhere in the way I wrote that in. So, let's do this again. Should only give me 800. I think I made a mistake there. Should we try that again? At least I know what the answer should be. See, we all make mistakes. Let's do the top part. 0.08 squared times 0.08 squared. That gives me that answer, and I'm going to divide that by what I'm going to cheat here a little bit. So I'm going to go 0.044 squared times 0.04 squared. It's the same thing. Oops. 4 squared times 0.2. Oh, and I didn't like that either. I'm doing well here. Got to get 800. No, we can. I'm just showing you. So we all have issues with calculators, and I am doing this on a board. Okay. Ooh. Different answer than I got just now. Do you see that?
Yeah.
Okay. Divided by. Come now. 0.04 to the power. To the power of 4 times. Oh, you said I want that. Okay. Times 0.2. Ah. See?
Bracket.
This is why I worked this out before we do this. Because also, even if I hadn't have worked it out before this grade 12s, I would have known that 8,000 was wrong. Okay, there's not a chance you're going to get an answer of 8,000 because that is ridiculously big. Okay, so it's 800. 800 is still quite big, but it's fine. Okay, there's nothing wrong with the value of 800. There's nothing wrong with the value of 0.8. But 8,000, I think, or was 8 million or 800,000, whatever it was, that was ridiculous. What does this Kc value tell me? Okay, the Kc value tells me that the equilibrium lies to the right. Okay, means that I have lots of product. Okay, lots and lots and lots of product when I get to the end. I don't have that much reactant, but I have lots of product because it's greater than 1. Okay, now from here, if we wanted to, if we were being particularly mean, we could now ask you questions about how to shift equilibrium. What would happen if I changed pressure or temperature and that sort of thing? What would happen to the equilibrium constant? All of those sort of things, grade 12s. So make sure this isn't the end, okay? If you can't do this, but there's still more questions underneath here, go and do them. Don't stop at this point and just leave it, okay? Leave space for it, leave enough space, even if you leave an entire page, okay? Go to the next set of questions and carry on, because probably after this there'll be explanation questions. What happens if you change equilibrium? What happens to the shift? And those are all your Le Chatelier questions, all the explanation questions, which we don't like, I know. Okay, but I think now that we've spent a long time on one question, it's time for a short break.
Okay, cool. Before we take a break, I'd just like to send a shout out to TK, Pearl, Vusi, Princess, Deboho, Sfiso, Sfundo, Blai, Kabelo, Tiamo, Pilangezwi, Nyakalo, and Gileabedzo. Thank you so much, Mindsetters, for tuning in and for sending your questions and for giving us a shout out. Shout out right back to you. So we are going to take a very short break, so don't go anywhere. Welcome back, Mindsetters. I so wish you guys had an earpiece with you at home so you could hear how people count when we are supposed to go on air. But anyways, Tracy, you have a question.
Yeah, I know. We're giving our director a heart attack. Sorry,
we are
Jane.
exposing you, director. But anyway,
Yes.
Tracy, you have a question from Pearl.
Yes.
For question 3.2.1, aren't you supposed to make reference to T2 and not to T1 and not T2, making it greater than since it's steeper.
Okay. It doesn't actually matter which way around you do it, Sweet Pea, because I said compare the rate. Okay, I've gone T2. Okay, I know what you're trying to say, and actually, I would have you correct. T2 is smaller than T1. I probably should have written that first. In the official memo for this, but thank you for pointing it out, you could actually do it any way around. It didn't actually matter. So I would actually say, and this is a good point, Sweet Pea, is rather say T2 smaller than T1 or T1 greater than T2. That's fine. Okay, it's just because of the way I read it. But that's okay. But thank
cool.
you.
All right. And then Sfundo Faela is asking, can you please explain the collision theory precisely?
Precisely. Well, precisely, I can do it in 3 lines.
Okay.
Number 1, particles must collide. Number 2, particles must collide with sufficient energy. And number 3, particles must collide with the correct orientation. And that is collision theory. Okay? So when we talk about rate and you asked to describe it in terms of collision theory, you've got to talk about the fact that the more often they collide, the more likely they are to collide effectively, which means in the correct orientation. As soon as you add things like catalysts and change temperature, you giving it sufficient energy or not giving it sufficient energy. So when we reduce the temperature, we are taking energy away, which means less particles have sufficient energy. When we increase the temperature, it means more particles have sufficient energy. But basically, particles must collide, they must collide with sufficient energy, and they must have the correct orientation.
All right. Shout out to Gabriel and Dineo for actually answering Sfundo correctly. And then TK.
Yes.
I'm not sure which question he's referring to, but I'm sure you'll know.
Yes.
I'm lost. How did you get the equilibrium? And then in brackets, he writes moles.
That's from KC. That's from the way down here. Okay, sweetie, because when I looked at the change row, which hopefully you didn't have too much of an issue with, okay, I then took the amount that I started off with the reactants. So I took the reactants, I minus 0.2 from it, 0.8, and that gives me 0.2. I read off the 0.1 from the graph. I started with 0 product, added 0.4, which gives me 0.4. Started with 0, added 0.4, which gives me 0.4. Okay, so I got it from the table. It's about as much time as I can spend on that.
No, it's cool. Those
okay.
are all the questions we have.
Now, we actually have another part to this question, which says the temperature is now increased. How will this change the value of the equilibrium constant? Remember, right at the beginning of this question, we said that the forward reaction is exothermic, okay? Temperature is increased. An increase in temperature always favors the endothermic reaction, okay? For this particular reaction, the endothermic reaction is the reverse reaction, which then means we favor making reactants. Okay, so that means we're going to increase the concentration of the reactants, which then says to me that because reactants are at the bottom of that equation, my Kc value is going to decrease. Okay, it's going to get smaller because I'm favoring the reactants. Okay? Then, how will each of the following affect the equilibrium concentration of Cl2? Water vapor is added to the container. So let's go back to the equation. Okay. Water vapor is added. We're increasing the amount of H2O. By increasing the amount of H2O, we're going to need to use it up. We favor the reactants, which means we have less Cl2. Okay. So we're going to decrease. So what happens here is this decreases, okay? If we add a catalyst, does absolutely nothing for the Cl2 concentration. By adding a catalyst, we just get equilibrium faster, so it remains the same. The volume of the container is increased. So we go back to our equation, which is over there. We now increase the volume, okay? So by increasing the volume, let's just remind ourselves this is actually O2. That's terrible. We are decreasing pressure, okay? that means the reaction favors the part of the equilibrium that has the most number of gas particles. We're going to favor making the reactants because there's 5 particles on the left, 4 on the right. So by increasing the volume, we decrease pressure, favor making reactants. So that means the Cl2 concentration will decrease. We'll have less. Okay? And what we're going to do is we're actually going to go into something that's very similar to this. We're going to go on to question 4, and this was actually the second part of a question from the 2010 paper. It says the reaction below represents the catalyzed step in the contact process. SO2, O2 goes to 2O3, delta H is negative, so that means it's exothermic. The reaction takes place in a closed container, reaches equilibrium at 427 degrees Celsius. How will a higher temperature, so in other words, increase in temperature, affect each of the following? Number 1, right, only increase, decrease remains the same. The rate of production, so we are increasing the temperature, that means more particles will have sufficient energy, therefore we have more effective collisions, it will increase the rate. So this increases the yield of SO3. In other words, how much SO3 are we going to have? We've increased temperature. Increasing temperature always favors the endothermic reaction. The forward reaction is exothermic. So by increasing the temperature, I'm favoring the endothermic reverse reaction because I want to get rid of the heat. Okay, by favoring the reverse reaction, I end up with less SO3, so my yield gets smaller. Okay, and in fact, this is one of the reasons why we make a compromise. This is an industrial process, so we make a compromise here, and we do this at about 450 degrees Celsius because we're making a compromise between temperature, between rate and yield. Okay, it might go really quickly, but we don't get very much. So we've got to be careful. Okay, so we make a compromise. Now, we're going to skip a little bit because I'm not going to do the Kc value on this one. Okay, we'll come back to it if we have time. This is question 5, and the numbers are a bit funny, but don't stress about it. Electrochemistry. Now we get to redox. Now we get to the stage where you go, oh, Joycey, please don't do this. This is not fun. I know, but it's okay. We can do this. We're going to take deep breaths, okay? Says to us, the cell notation of a standard cell, okay, a standard galvanic cell containing an unknown metal electrode is shown below. Name the components of the cell represented by the double vertical lines in the cell. So we have unknown metal going to solid, going to X3 plus, that's its ions. Then it has whatever that means, and we go to the next side with all the conditions. So that double line is the, I can hear it, salt bridge. Okay, remember, the salt bridge is a very important part of our cell because the salt bridge gives us the ability to complete the circuit, number 1. It gives a path for the ions to moving, number 2. And number 3, it maintains the neutrality of the half cells. Because without it, the half cells would gain a charge, it would lose its potential, the reaction would stop. Okay, so it maintains the neutrality of the half cells. Then they say to you, what are the 2 standard conditions that are applicable to that half cell? Okay, so only to this part of the cell. Now, please be careful. There are 3 standard conditions. 1, the pressure must be 1 atmosphere. 2, the electrolytes must have a concentration of 1 mole per decimeter cubed. And 3, the temperature must be 25 degrees Celsius. 3 conditions. They say, of those 3, which 2 are applicable over here? There is no gas involved. Pressure is not a standard condition for the cell. There are no gases. So if you put pressure here, you're going to get it wrong. So the standard conditions that they're looking for here are the Pb2 plus concentration must be 1 mole per decimeter cubed. Okay, your electrolyte must be at 1 mole per decimeter cubed, and the temperature must be 250 degrees Celsius, or you can write it as 298 Kelvin. Okay, that's fine. Now they say identify the oxidizing agent in the above reaction. So now we've got to go, what are they asking for? Oxidizing agent. Okay, oxidizing agent means identify what is reduced. Let's remind ourselves that oxidation, if something is oxidized, it's going to lose electrons. If something is reduced, it's going to gain electrons. Your oxidizing agent causes oxidation and is itself reduced. Your reducing agent causes reduction and is itself oxidized. Okay? Your anode is where oxidation takes place. Your cathode is where reduction takes place. So they're asking me what is reduced. Now this is in standard notation. Standard notation always says to us that it must go from anode to cathode. No exception. Must go from anode to cathode, which then means that at the cathode, the Pb2 plus ions are reduced to Pb, not lead. Please be careful here. It is the lead ions, the Pb2 plus ions that are gaining the electrons. So when I say here, what is the oxidizing agent? It's the Pb2 plus ions. You can write it as the lead 2 ions, but you cannot write it as lead. The metal is not reduced. Okay? The ions are reduced. Now, the initial reading on the voltmeter connected across the electrodes of the above cell is 1,53 volts. Identify metal X by calculating the standard reduction potential of the unknown metal. All right, so now we're going to sit here and we're going to go, okay, I have a voltage in there somewhere, and now I've got to do some stuff. And how many of you going, no, Dad, I would leave this one out? Of course you would. Don't. You go to your information table, and you realize that you have 3 equations, and the one we're going to use says to us that the voltage of my cell is equal to the voltage from my cathode minus the potential of my anode. Okay? All of you from across the country are going to be being told to use different redox tables. Some of you are going to be told to use table 4A, some of you are going to be told to use 4B. I use 4B because traditionally that's what I've always used. It really doesn't make any difference. Please make sure that you use the one you've been taught to do. We will use 4B, okay, where we have the higher reducing agents at the top, okay, because that is the way traditionally in Gauteng we've used it, okay. But what we're going to do, grade 12s, is I'm going to leave you hanging because I can. But Looney's not liking this. So while you go and find your redox table, because you need to have one in front of you, okay, and I didn't warn you, you're going to go find the redox table that you need, okay. I'm going to leave this here, and I'm going to leave you. So for the next break, and you've got about 2.5, 3 minutes, okay, you're going to identify what the metal is, okay. So I'm going to leave it at that, and then we're going to take a short break, and then they're going to identify what metal we have.
All right. Mindsetters, before we take a break, I'd just like to read something here. It's from Percy Sky Reed, and he says, "Hey guys, I'm here in Zimbabwe, and I didn't go to school today, but hey, it's quite interesting because I'm benefiting a lot from Tracy." Thank you for watching all the way in Zimbabwe, Percy. Mindsetters, with that said, we will take a break, and we'll see you straight after this. Welcome back, Mindsetters. We are in the last leg of this very fun physical sciences race for chemical change grade 12 spring school. You know how I just like to put in the rest thing there. So we do have our competition going on. So what we're going to do now is that we're going to stop the clock. So you need to make sure that you have been entering all your favorite numbers and all of that. So what Tracy's going to do is just go onto our Facebook
And
page
we're going to refresh.
And yes.
Okay, let's see what we get. And
7.
7 is the lucky number today.
So mindset has it's
Hey,
done.
that was my lucky number on Tuesday. I would have won on
Really?
Tuesday.
Yeah. So mindset is done for this show. 7 is our lucky number. All the 7s out there who tagged and shared the post and told us that 7 is your favorite number, check out 4 o'clock. You could stand a chance to win. Watch our show. During the show, we will announce who the winner is. So all the 7s out there, hope you guys stand a chance to win that very special Learn Extra hamper. So Tracy.
Oh, I should have been here on Tuesday, man. So I'm not allowed to win. That's actually quite rude. You know that, hey? It's like when we had the whole, what was the Earth thingy? After Earth thing, and I wasn't allowed to win. I didn't even get tickets.
No, you just can't.
It's rude. I'm sorry. So you best be entering. Anyway, so you had to go and find your redox tables. Okay, so now what we're going to do is, first of all, we knew that the cell was 1,53 given to us. The cathode, we've identified the cathode because we know what was reduced. That was the lead. So if you go into your redox table, which we don't have one for you to look at, but if you go into your redox table, because I have one here, the cathode has a value of minus 0,13. Please remember here for me, grade 12s, this is really important. Even if you swap an equation around off your redox table, you don't ever change the sign from the potential. Okay, don't ever change the potential sign. You must leave it as it is, okay? So this gives us, we would get the anode value from here, and what happens is if you work all of this out, so we take the minus 0,13 over, and I have to write a little bit smaller, that gives me 1,66. That's minus for the anode value, which means the anode value is, it's a good thing I can spell for you, is minus 1,66 volts. You now go and you look on your redox table and you literally look down that last column, you find this minus 1,66, and what do you see? You see that X is actually aluminium. Now there's another little hint that I know that I'm right, because look over here, and this is what's nice about this. Aluminium is in group 3 or 13, depending on how you learned the numbers. It has a valency of 3. It's going to lose 3 electrons. So I know I'm right. It's not X2. Okay, so it's aluminium. Then they say write down the balanced equation for the net or overall reaction taking place in the cell without, omit the spectator ions. Well, we know what happened is that aluminium is being added to lead 2 plus, and it's becoming aluminium 3 plus lead. But that's not the balanced equation. So what we need to actually do is we look on our redox table. We're going to do this in more than one step, so I'm going to do it at the bottom here so you can see. What happens is aluminium is being oxidized. So aluminium 3 plus has 3 electrons. The lead 2 plus is being reduced, but it only gains 2 electrons. You get this off your redox table. The issue here is that you need to make sure that the number of electrons are the same. So I'm going to take this equation times by 2, this one times by 3. I'm rewriting it. I want to make sure that I know exactly what I'm doing. So this is 2Al, which then becomes 2Al3 plus 6 electrons. This is 3Pb2 plus 6 electrons, goes to 3Pb. Now the reason why I've done that is these electrons cancel out, okay, which then means my net equation, which is what they wanted without the spectators, is 2Al plus 3Pb2 plus, which goes to 2Al3 plus 3 lead. Okay, now it's a balanced equation. Guys, please be careful here. If we were adding this, putting in the spectators, it would make more sense why we need the 3s and the 2s. So a spectator could be something like a sulfate or a chloride or something like that, and that helps us with the balancing. But this is, you didn't need it. What they were looking for is, did you recognize that you needed to balance the number of electrons? Okay? So if I go back here, this needed to be 2, this needed to be 3, this needed to be 2, this needed to be 3. Okay? Now, how will the initial voltmeter reading be affected if the concentration in the X3 plus now increases? Okay? So the electrolyte concentration increases, and they want to know what happens with the initial voltmeter reading. By increasing the concentration of the electrolyte, we have changed our standard condition. Standard condition says that we have to have 1 mole per decimeter cubed. We've increased the initial concentration, which then tells me that we're actually going to increase the initial voltage. Okay? Write down the value of the reading on the voltmeter when the cell reaction has reached equilibrium. 0 volts. When it reaches equilibrium, the battery has gone flat. Okay, there's now no longer a potential between one side and the other. Okay, so, Noonie, are there any questions?
Let's quickly.
Because I can go back to another question that we sort of skipped over.
Oh, yes, we do.
Yes.
Mabunda Polite is asking, what do we start with when writing net cell reaction, anode or cathode?
It doesn't matter, sweetie. Oh, you mean the cell reaction or the cell notation? If you mean cell notation, then it does matter.
Cell reaction.
Okay. The cell reaction makes no difference. So over here, when I wrote down the cell reaction over here, okay, it makes no difference. Absolutely no difference whatsoever, up to you. I tend to write the anode first because I tend to write the oxidation half reaction first when I'm working it out. Doesn't actually matter. Cell notation does. Cell notation must be written, where is it? At the top here. Anode to cathode. Cell notation absolutely makes a difference. Cell reaction doesn't matter. Okay. Anything else? No? Okay. So, I don't think I'm going to get to actually finish this one, but I'm going to start you off. Okay, and I'm going to give you what the answer is. And the reason why I don't think we're going to quite finish is this is a horrible maths one. Okay, but I'd rather start you off, and I want you to see what happens when you get stuck from a maths point of view, because I think it's quite important. This is a mean equilibrium question. I'm horrible, hey?
No, not that bad.
The examiner was horrible this year, that much I can tell you. So, the reaction of this is the SO2. So, the reaction we're looking at here is SO2 plus O2 gives me SO3. Okay, so this was the balanced equation. The reaction is investigated on a small scale, and initially 4 moles of SO2 and an unknown mass of O2. This is the part we don't like. So what we're going to do here is let's highlight it and go unknown. Ooh, horrible. This is the yucky part, but it's okay, we're big. Sealed in a container, and this is what Duncan was asking about earlier, is I really do need to know volume. 2 decimeters cubed. So Duncan, I hope you're paying attention. It's allowed to reach equilibrium. At equilibrium, it's found that the concentration of the SO3 is, so the SO3 now has a concentration of 1,5 moles per decimeter cubed. Calculate the mass of O2 initially present in the flask if the Kc value is 4.5. All right, so let's set up our value table, okay? So we know we're going to have our table. We have the initial, we have ratio, we have initial, we have change, we have equilibrium, and it's going to go a little bit further, so let's just do this quickly. Let's do this. Okay. Okay, and SO2, O2, we're going to put in my line, and that's SO3. So this is SO2, O2, SO3. This is my ratio, remember, we then have initial, which we really need to have as in moles, okay? We have our change, we have equilibrium, number of moles, and we have equilibrium in concentration, which is moles per decimeter cubed. So, first thing I'm going to do is let's write in everything we absolutely know, okay, which I'm going to put in green. We know that we don't start with SO3, so there's no SO3. We know that we initially had 4 moles of SO2, okay, and then we know right at the end there we have 1,5 moles per decimeter cubed of SO3. We also know that the volume of my container is, where's it? 2 decimeters cubed. Okay, and I know the Kc value, but we'll get to that. So now we've got to go, okay, let's, oh, sorry, I put those in the wrong place. I've just realized that should be there, that should be there. And I'm pretty sure somebody's busy screaming at the TV going, Tracy, you silly girl. And this was 2, this is 1, that's 2. Okay, so let's work backwards a little bit, okay? If the concentration is 1,5, remember concentration is, so I'm going to put it over here, concentration is number of moles divided by volume. So if that's 1,5 and my volume is 2, then my number of moles, let's just quickly do this. Okay, just because now I'm writing. 1,5, volume is 2, so that means I have 3 moles, okay, hopefully I haven't lost anyone. Let's put this in another color, so I know that's 3 moles, okay, which then means that if I started with 0, ended with 3, I added 3, okay. My change line must be the same ratio as my ratio line, so the SO2 is easy, times by 2, divide by 2, that gives me 3. Here, times by 1, divide by 2, this is 1.5. I haven't lost anyone yet. Then I'll go 4 minus 3, which means I've got 1 mole per decimeter cubed at the end here. Here is my problem. I didn't know how many moles of oxygen I had. So you know what? Let's make that X. Give it a value. Okay, we're going to come back to it. So that means over here, this is X minus 1.5. Okay? When we want concentration, we're going to divide each of these by 2. So this is 0.5. And this is X minus 1.5 divided by 2. This is where life gets a little bit hectic. Now, hopefully I haven't lost any of you because we've done the same thing over and over again, grade 12s. But there's an X in here. And that's okay because I knew what the Kc value was. Because over here, my Kc value is 4.5. And we remember that Kc is concentration of my products divided by concentration of my reactants. So that's what we've got. So now we've got 4.5, which is going to be equal to 1.5 squared divided by 0.5 squared times X minus a half divided by 2. Okay? This is completely a maths problem from here. Okay? Completely and utterly a maths problem. You have to solve for X. I know this becomes a nightmare, but what happens, grade 12s, if you get to this point and now you're looking at this and going, right, you say just that and you move on. Okay? You have got 90% of the marks for this question. From here, you would need to work out the mass, because they wanted the mass, okay? Not the number of moles, the mass. And remember, number of moles is mass divided by molar mass. So whatever X is, it's equal to the mass of the oxygen divided by 32. Okay? So we can work out the mass if I know what x is. This is completely up to you because it all depends on how you've been taught how to do fractions. I do all sorts of weird and wonderful things from here, and what we're going to get here is that x equals 5.5. We don't have time for me to do the maths with you. I'm sorry, grade 12s, but you need to be able to do that. And also, I think you need the practice, okay? So you get 5.5 moles. So that means n equals m over m. This is 5.5 equals m times 32 gives me 176 grams. I'm done. And in fact, on the mark allocation, if you didn't get to this part, so up to here, you only lose 3 marks for this last little thing. This was worth about 9 marks. You got most of the marks, grade 12s, okay? So please don't get freaked out by it. Follow the steps I did, which is, and you can see in the different colors I did it in. I set up my table, which is the yellow. I wrote in everything I knew, which was the green. I then started to work backwards, which is the purple, okay? And then I added in my unknown. Always easier to do that. And what do you need to remember? The ratio line and the change line must be the same ratio, 2 to 1 to 2. Okay, quickly, Looney.
Yes.
Are there questions? There must be.
Can you just...
Oh, okay, I'm just going to have to talk rubbish for a little while. It's fine, because you've got to get your questions in quickly, guys, because we're almost running out of space. What do I need you to remember from this section, grade 12s, is it's practice, practice, practice. We didn't do too many questions on answering questions according to Le Chatelier,
Yes.
but you've got to be able to do it. Quickly, yes.
Can you
questions.
please explain, this is from fellow Dauntless, okay?
Okay.
Can you please explain rate law to me clearly? The rate law.
Rate law.
Yes.
I don't actually think I know what that is.
Okay. And then...
Yeah.
Okay. And then Kelani says, I think you've made a mistake with inserting the information given on the table.
Where?
Didn't specify.
So you got to, I don't think I did. I'm just going to check my answer with what I've got there.
Yeah,
No.
That's about
Sweetie,
it.
I'm going to need to know what information you're talking about. I promise, go look back at it. According to the memo I've got and the stuff I did at home, because I do this before I come on air, just in case, because I absolutely can make mistakes, and I don't mind you correcting me. In fact, I made a mistake on Tuesday, and I got corrected. I really am happy with that, because it means you're awake, but I know I haven't made a mistake on this one. So maybe go back and re-look at it. The notes are hopefully on Facebook.
Yes.
But also maybe what's a good idea, Sweet Peas, if you're still not getting it, wait until the video gets downloaded and then go look at it again. But I'm actually running out of time, so I have to say goodbye. Guys, I'll see you before your prelims. We're going to do some prelim review. Well done for being here during the holidays, and I'll see you soon.
All right. Thank you so much, Mindseters, for tuning in. Tracy said it all. Thank you for tuning in. Well done. Everything. All the best for your finals, and we'll see you soon. Goodbye.